Gee whiz, it's Christmas! Dad, what'd you get me?
Merry Christmas, son. Your present's under the Christmas tree.
Whoa, it's a laptop?
Open
Cool.
it, son.
It's my favorite, the breaking of epoxide rings under basic conditions.
Hey everyone, today I'll be discussing the history, uses, and mechanisms behind the opening of epoxide rings while under basic conditions. So below is the general scheme behind the reaction. In the scheme, you can see that there is a 3-atom ether ring, otherwise known as an epoxide, and it's going to be opened by a nucleophile as well as it's going to be being protonated by some kind of acid. So first I'll be diving into a general history of the reaction, just to give context before we go over the general mechanism. The reaction was first discovered in 1984 by the Jameson group in the form of epoxide opening cascades. These cascades are pictured below and involve long chains of epoxides opening to either form other cyclic rings or to take in other functional groups. The number of products that could be synthesized using this method was dramatically increased when in 2001, a Nobel-winning method of creating epoxy alcohols was discovered, and it's shown here, and it's called the sharpless epoxidation method. So going into the uses, the opening of epoxides is mainly done in order to create a variety of products with different functional groups. A common example is the compound propylene glycol. The reaction scheme is shown below, and it's a pretty common product with around 2.16 million tons produced every year, and with uses in both the EU and in the US. It is a common water-absorbing compound that can be found in ice cream and other pharmaceutical products, and this just goes to show how commonplace the use of epoxide opening rings is used for our everyday products. Besides products, we also use it for safety purposes just due to the fact that epoxides can be dangerous mutagens. It can be sometimes important to break up the epoxide rings in order to use them safely in labs and to put them in other products. So moving on to our mechanism, we're going to be converting 2,2,3-trimethyl oxyrane into 3-methoxy 2-methylbutan-2-ol. So as you can see, epoxides are highly reactive and unstable structures due to the fact they have high ring strain and that the oxygen is more electronegative than the two carbons. This makes it so that the carbons will have a partial positive charge while the oxygen will have a partial negative charge. Because of the partial positive charge, strong nucleophiles will be attracted to the carbons and will want to attack it. But this begs the question of which carbon will accept the electrons. Because we are working with strong nucleophiles, the reaction will be SN2, and because of this, we'll attack the carbon with the least steric hindrance, or in other words, the carbon that is the least substituted. In this case, that carbon will be the right one. This attack causes the electrons from the carbon-oxygen bond to migrate to the oxygen, leaving it with a negative charge. In order to get rid of this negative charge, an alcohol will act as the acid, and acid-base chemistry will be carried out, so the oxygen will be protonated, leaving it as an OH group. This process will finally get us to our desired 3-methoxy 2-methyl-2-butan-2-ol. And that is basically all the steps in this mechanism. Finally, here are the sources to all the information I talked about today, the history, the mechanism, and the uses. And as always, because this was a Christmas themed video, Merry Christmas.